Hello everyone and welcome back to my channel. Today I'll break down why C0, that is, the sequence space consisting of all sequences of real or complex numbers that converge to zero, is a Banach space through the realm of functional analysis. Let's get started. To begin, let's precisely define C0. This space consists of all sequences of real or complex numbers that converge to zero. Formally, a sequence x equals xn belongs to C0 if limit n tends to infinity of xn is equal to 0, that is, xn tends to 0 as n tends to infinity. Now, what makes C0 a Banach space? To answer this question, we need to understand two key concepts: normed vector spaces and completeness. Firstly, C0 is a normed vector space. This means it is a vector space equipped with a norm that satisfies certain properties. Also, it is a subspace of the space of bounded sequences, denoted by L infinity. So for C0, we use the sup norm defined as norm of x infinity equal to supremum of mod of xn for n in the set of natural numbers. This norm measures the size of a sequence by taking the supremum of the absolute values of its terms. The sup norm satisfies all the properties required for a norm: positivity, scalar multiplication, the triangle inequality, and positive definiteness. Next, we consider completeness. A space is complete if every Cauchy sequence in the space converges to a limit within the space. A Cauchy sequence is one where the elements become arbitrarily close to each other as the sequence progresses. To see why C0 is complete, let's take a Cauchy sequence xn in C0 under the sup norm. The sequence evidently has elements of C0, where each element converges to 0. Then xn will also be a Cauchy sequence in the space of bounded sequences L infinity, as I've mentioned before that C0 is a subspace of L infinity. Since L infinity is a Banach space, its every Cauchy sequence converges to a limit in L infinity itself. So, xn converges to x, where x is an L infinity in the form of a bounded sequence. At this point, we aim to demonstrate that x belongs to C0, that is, x is a sequence converging to 0. As x and all xn's are sequences, we can write xn as the sequence xnj and x as the sequence xj. Now, referring back to my earlier point, by using the definition of convergence in normed spaces, for every real epsilon greater than 0, there exists a natural number n1 such that the sup norm of xn minus x is less than epsilon over 2, where each n is greater than or equal to n1. Let's revisit the definition of sup norm. We observe that the sup norm of xn minus x is the supremum of mod of xnj minus xj. So this implies that mod of xnj minus xj is less than epsilon over 2 for each j greater than or equal to n1. Considering that xn is a Cauchy sequence of C0, that is, all of the terms of a sequence such as xn1, xn2, xn3, and so on converge to 0, we again use the definition of convergence for xnj. For every epsilon greater than 0, there exists another natural number n2 such that mod of xnj minus 0 is less than epsilon over 2 for every natural number j greater than or equal to n2. This in turn becomes mod of xnj is less than epsilon over 2. Then we finally show that xj converges to 0. Here we add and subtract the value xnj to mod xn minus 0. Applying the triangle inequality to it, this is less than or equal to mod xj minus xnj plus mod xnj. As we proceed, let's recall what was previously stated about the sequence xnj. 1. For every epsilon greater than 0, there exists a natural number n1 such that mod xnj minus xj is less than epsilon over 2 for every natural number j greater than or equal to n1. And 2. For every epsilon greater than 0, there exists a natural number n2 such that mod xnj is less than epsilon over 2 for every natural number j greater than or equal to n2. Using these two assertions in these two terms, this expression is less than epsilon over 2 plus epsilon over 2. And then we get this equal to epsilon for every natural number j greater than or equal to n, where n is the maximum of n1 and n2. Hence, we obtain mod xj minus 0 is less than epsilon for every j greater than or equal to n. This means that the sequence xj converges to 0. So, x, which is the limit of convergence of the Cauchy sequence xn, lies in the C0 space. And consequently, we have derived the necessary outcome that every Cauchy sequence of C0 converges to a limit in C0 itself. Ultimately, we've established C0 is a Banach space. Hence, with its completeness and the norms framework, C0 stands as a quintessential Banach space in the study of functional analysis. And that's the end of the video. If you enjoyed this video, please give it a thumbs up and subscribe to our channel for more content. Don't forget to hit the bell icon to get notified whenever I upload new videos. Leave a comment below with your thoughts or any questions you have. See you in the next video.